computer. Okay.
Okay.
Cool. So I think we can probably start. So hi everyone, and thanks for joining us again on another live podcast of Al-Khalal, or another live episode of Al-Khalal. This episode is possible with the help of the Ramon Foundation and the Horizon community and the Israeli Space Agency. So a big thanks to all of them. And another big thanks to Ronnie Kowalski, who offered, actually he offered me to do this talk, and he connected me with Simon. So thank you very much, Ronnie. For whoever doesn't know me, my name is Ben-Zaav, and today we're going to talk about search for extraterrestrial intelligence, or in short, SETI. Our special guest for today is Dr. Simon Steele. And Simon is the Senior Director for Education and Outreach at Seti Institute. So hi, Simon. Very great having you with us.
That's good. Yes, yeah. It's a shame it's not in person, but the wonder, one of the silver linings to the cloud of the global pandemic is that we've learned to communicate globally. So it's great seeing people from so many different locations.
That is true, and I'm sure that we will manage personally as well. Mm-hmm. You know, the pandemic will be behind us, and you will come and visit us in Israel.
Yep. That would be good.
So a little bit about you. You have a bachelor's and a master's degree in physics and a PhD in astrophysics. But looking at your resume, you have another big love, and that is education. Am I correct?
That is true. I've sort of, my career has alternated between education and science, and I'm lucky that in my current job, it's allowed me to sort of combine both. I've always enjoyed the research aspect of astronomy, but also sort of the sharing the amazing ideas, you know, either through teaching formally or to members of the public through museums and presentations and so on. And my current role is really, you know, that interface between the research science that is going on at the Seti Institute and the public for events like this. So it's great. It's a dream job. It allows me to pick up two of my loves. You know, if we could work in football, then that would be perfect too. But we can't. So yeah.
Great. I'll just ask everybody who joins us to mute himself, or Roy, if you can mute. You're a co-host, Roy, so you can mute whoever you want. Just don't mute Simon or me. So
unless you don't like what I'm saying, then you can mute me. Yeah.
Everybody who is here, I think, wants to hear what you're saying, so it's okay. We're going to have a talk, and then after the talk, we're going to have a Q&A session. So, you know, there the audience can actually come up with questions. You have questions, guys, just write them down in the chat, and when we get to the Q&A session, we can either, you know, let you talk and ask your question, or you can ask the question for you, whatever fits. So let's start. And I think the best thing is maybe for us to understand what SETI is, Search for Extraterrestrial Intelligence. What is that?
Yeah. The name is very clear, and ultimately I'm going to do that's it. That's all I've got to say. I'll draw a distinction in a moment between SETI as a science, the search for extraterrestrial intelligence as a research science, and the Seti Institute, which by its very nature obviously does SETI research, but also does a whole lot more. And so maybe just a little bit about the origins of the Institute, and therefore SETI itself. The Seti Institute was founded just over 35 years ago by a couple of scientists who are now retired but still involved in the Institute, Jill Tarter and Frank Drake, and those names may be familiar to you. Jill Tarter may be more familiar to you as the character Ellie Arroway from the movie Contact, which was based on a Carl Sagan book, and Carl Sagan was involved in the Institute in the early days. Frank Drake is famous for what's called the Drake equation, and we can say a little bit more about that, because that is basically the spine or the skeleton of SETI, the SETI search itself. Institute was founded in 1984 to search for what we call technosignatures. That is signals and using radio, the radio part of the spectrum in those days, and it still mainly is, that are artificial, that is, are created by intelligent civilizations rather than natural radio signals. There's been a lot of false alarms in the history of astronomy for things that were thought to be artificial but turn out not to be. There were pulsars, the first pulsar, which is a spinning neutron star emitting very, very regular pulses. Nobody knew how nature could do that, but it turns out nature can do that. Then there were things called quasars, and more recently we've had objects called gamma ray bursts, and we can talk more about these objects as astronomical objects, and fast radio bursts. All of these items were initially thought to be non-natural but turned out to be natural. So Frank Drake, who initially did the research, would chose some target stars to point a radio telescope at. They used a big radio dish in Green Bank, West Virginia, and to see if any signal would be received from those stars. Of course, back in the 1960s, when the original SETI work was done, which is 20 years before the Institute was founded, nobody knew that whether stars had planets going around them. So this really was literally a search in the dark. No signals were detected. They did detect one that they think was a military plane. The US has never confirmed that they identified a military plane flying over, but that's
or denied.
Or denied. So that's probably what it was. And that has been the way that SETI research has mainly been done over the years. It's looking for signals in the radio spectrum for various reasons. And again, we can talk about that, to search for technosignatures, that is signals that could only be produced by non-natural means. And that search goes on. The level of sophistication has gone up, but the technique has remained. There are other types of SETI searches. There's what's called an optical SETI search that is looking for a similar thing in the visible part of the spectrum, which turns out to be much more difficult, but there are programs that do that as well. And of course, now with the technology of mainly computing power, you can record so much more data over so many more different frequencies of radio waves. That you're talking terabytes and petabytes of data coming in to search the radio sky for these technosignatures. There's been a few false alarms, and we can talk about those. But that's basically the idea of SETI. And should that detection be made, that is another story altogether of what is the protocol should something be proven to be non-natural. And there are protocols in place. So that is SETI itself. The SETI Institute is much broader than that for various reasons. One is that there is no federal funding for SETI research. That was stopped in the 1990s. The US government does not fund the search for intelligent civilizations or intelligent life. It does fund the search for life. As you know, from the Mars rovers and new missions that are coming up to Jupiter's moon Europa, there are big searches for life in the universe, but not intelligent life in the universe. And so a large part of the SETI Institute's role now is in what is called astrobiology and the search for biosignatures. And many SETI Institute scientists are involved, say, in the Mars rovers. They're involved in the mission to Europa, Europa Clipper. There's a big interest in the missions that are going to Venus because there was a potential signature for a biosignature, a chemical
in the clouds,
misequilibrium in the high clouds of Venus. So these are all the areas that the Seti Institute is involved in, as well, of course, as pure searching for alien civilizations. So that's an overview of Seti.
I want to take you a step back, because we talked about what happened after the institute opened, but actually Seti is something that happened, even 100 years ago, maybe with less technology than today. But as you said, funding stopped somewhere in the 90s. So can you shed some light on what happened, maybe not 100 years ago, but I don't know, 30, 50 years ago?
Yes, I suppose, I mean, the Seti as a science, I mean, the search for intelligent life in the universe is very, very old. And the concept of technosignatures, the sign of technology elsewhere, is a very old process as well. You can go back to Percival Lowell in the 19th century, who thought that there was an identification of canals on Mars. Canals, which was a mistranslation from the Italian. The word channels happened to be canali in Italian, and that was translated in English as canals. The concept of a canal, of course, is an artificial waterway, and so the appearance of Percival Lowell's canal system on Mars is an example of a technosignature identification. It's also, just to digress a little bit, it's an identification of what we refer to as an artifact. You're not actually communicating by finding canals on Mars, which of course we know they didn't. That's not actually a communication with an alien civilization, but it's the identification that there is an alien civilization there, let's say, and then that turned out to be a false identification. But this search for artifacts, the recognition of something that is artificial, is another method of SETI research. And what's very interesting is, as I said, NASA does not fund SETI search. It did very recently fund a SETI scientist to look for potentially for artifacts, alien artifacts. And by alien artifacts, we mean large-scale structures that are built around other stars, items that are called Dyson spheres. And these are the idea from a physicist, Freeman Dyson, is that a very advanced civilization could potentially harness the energy of its entire star by enclosing its entire star with a framework that will collect all that energy. That would, of course, have a severe effect on how we would view that star, because we would start seeing the star being blocked by these large things that this alien civilization is building. But that's something that's identifiable now, because, of course, with the latest planet hunting missions like Kepler, which is now winding down, and a new one called TESS, you can look for these dimmings of a star that could potentially be due to a very large artificial structure passing in front of them. And that is a proposal that has been funded to analyze test data for anomalous dimming of stars.
Wow, but it's amazing that they would sponsor something like this, but would not sponsor the regular big antennas that just look up and listen. But that has been happening for several, dozens of years, and maybe they decided that there's nothing there and the money should not go there. I don't know.
It's very difficult, and this, of course, it's not just limited to SETI research, but any science, because you are looking for something that you don't know exists. You have to let in a big extreme bad end of that. Does the Yeti exist in the forests of northern Canada or Siberia? I think. then that's an extreme case. You don't know, but you would like to provide a test. And maybe a better example is a type of animal that may or may not be extinct. That you would hunt for, and you need to look before you can confirm one way or the other. And the thing with SETI searches is we do not know if it's going to be successful or not. The important thing, however, is the more you look and the more you don't find, puts very strong constraints on how life evolves in the universe. We know that the Earth is a very, very unique place. Mars may or may not have had life in the past. Venus may or may not, probably doesn't have any life now. You have to look for these things because you have to set limits on how common these phenomena, the phenomena of life, is in the universe, and that's true for intelligent life. And the more you run these tests, the more sophisticated these searches become, and the fewer successes you have, the more negative results you get, is an important result in itself. It suggests that the ability for planets to host the evolution and development of life over long periods of time, to the point where you can develop an intelligent communicating system, is rarer. The conditions are not there, and that negative result is as important as a positive result. And I think that's important, but that when the funding ended, that was not an acceptable argument to the senators who made that vote.
So let's maybe take a step back and ask this philosophical question: why do we need to look for life in the universe? I mean, what's wrong here? This is good. Why should we spend all our time and money looking for something somewhere else?
That's a very good question. I think everybody in this room has their own answer, and maybe it'll be interesting to hear people's views on that at the end. I think the question is whether you separate life and an intelligent life away from the natural realm of a planet. If you look at the Earth, I think it's very obviously it's an integrated system, and that life, the biosphere, is very, very important to the long-term evolution of our planet. And it's true now as we enter the unofficially named Anthropocene era, where one species has a global impact on that world. It is obvious that the biosphere, including intelligent species, has a dramatic effect on the long-term evolution of the planetary conditions. And therefore it no longer becomes, are we interested in aliens or communicating, or are we alone? It becomes an important discussion of what could be a pretty standard planetary evolutionary process, that you have geology, you have geochemistry, you then have biochemistry, you then have technology feedback into a planet. And so saying, why should we study SETI to look for intelligent civilizations, is saying, why should we care about the weather systems on a planet? Why should we care about the winds on Jupiter? Why should we care about the history of oceans on Mars? It really is a continuum, and to remove the study for the intelligent species out of that is really taking out possibly a big chunk of the picture. We don't know how big a piece of the picture. You cannot study the history of the evolution of Earth without discussing biology or discussing the technology of one of the species that's developed on it. And so I think there's a fundamental science on planetary evolution and comparative planetology at the most basic level that has to include SETI. But I think it goes beyond that, of course. This is quite a philosophical question, is not just a scientific one. Are there other intelligent civilizations, or are we alone? This is a very, very deep fundamental question that I think it's important to put constraints on. You know, again, it goes back to our role as a species. I mean, are we, if we are unique in terms of intelligent civilizations, I think that but makes it much more critical that we actually preserve that. And by studying or getting in contact with other intelligent civilizations, maybe we'll get an understanding of the long-term survivability of intelligences, and that's key as well.
So I think. Oh, sorry, didn't want to cut you.
Carry on.
Sorry.
No, carry on.
So I just wanted to say that it would be interesting to see what people think. So I just put the grid view right now on so that I can see people and everybody can see everybody. And I would offer you guys to open your cameras, and whoever thinks that there is intelligent life out there somewhere, you know, let's raise hands and see how many people think it's there and how many people think it's not there, just for statistics, you know. So I'll wait for some other people to open the camera. Okay, so who thinks that there is intelligent life out there? So I think it's, yeah, probably most of the people that open the camera.
Yeah.
Okay.
I better put my hand up because they're paying me, so I'm going to raise my hand.
So okay, so
Yeah.
So now that we understand a little bit more about it, where is this being done? Where is SETI, not the Institute? We're going to dive into the Institute as well, but SETI, the science research, where is that being done around the world?
Yeah, there are very few institutes and scientists working on SETI. It's a very, very small part of astronomy research, and it's really only being done and it tends to be not exclusively but highly US centered for some reason. The main centers are the Seti Institute, UC Berkeley, Pennsylvania State University, to name some. There's been some work at Harvard through Avi Loeb. I'm sure you've all heard of he was here. Some of his theories. He was here
okay. in one of the episodes.
Okay, yeah, okay, yes, yeah. So most SETI research, it does still involve radio astronomy. There is a group called the Breakthrough Foundation that is run out of UC Berkeley. Yuri Milner. And they do a lot of SETI observations using telescopes in Australia, the Parkes Radio Telescope, and of course there was a recent potential signal detected from Parkes, and you know, we can talk about that. There's also the Green Bank Observatory in West Virginia, the Arecibo Observatory in Puerto Rico, which of course had their collapse last year, unfortunately, was used a lot for SETI research, both mainly you know, receiving signals, but also a famous transmission by Frank Drake back in the 70s that was beamed out. And the concept of METI, we'll come back to that, which is messaging extraterrestrial intelligence, is a controversial subject, of course. SETI is a passive science. That is, you're receiving information, you're not transmitting. The SETI Institute has its own set of radio telescopes in Northern California called the Allen Telescope Array. There are 42 dishes. Some of you may perhaps think that there's significance in choosing 42. We'll get back to that.
And so maybe I had a question about that, but if you're already talking about that, then maybe tell us, you know, why it's called Allen.
Yes, and this it was a grant from Paul Allen, who was one of the co-founders of Microsoft, who was very heavily into SETI research and funded the construction of the ATA, for short, the Allen Telescope Array. Originally, there was meant to be 350 dishes, but it costs a lot to build dishes. So we currently have an operational telescope of 42, which is doing some very good research, is doing astrophysics research, but it is also the only telescope array that is specifically designed for SETI research. And one of the things that's important about that is, of course, if we're talking about an artificial signal from a civilization, of course, we don't know what it's going to look like, because we're forever imposing human parameters on a search, which of course is completely ridiculous, because we can barely communicate with other intelligent species on Earth. We sort of got whales and dolphins down, but supposing that there's a more of a similarity with octopi, these sorts of things. So we're imposing this, but the assumption is that an artificial signal will be a very narrow band signal, that is like tuning, a radio show in, for those of us who are old enough to remember tuning radio dials, with a maybe a width of 1 Hertz signal. And so there are very few no natural phenomena that can produce these very, very narrow signals. So you're looking at a frequency. But if you look at say 900 megahertz, and the aliens are transmitting at 901 megahertz, you're going to miss that. You're not going to even pick it up. So what you want to do is look at a huge range, a band of those signals independently to pick up these narrow bands. And most radio telescopes are not necessarily designed for that, because they're more designed for looking for more broader signals, quasars, radio galaxies, and so on. But the Allen Telescope Array is designed to look at these a lot of very distinct frequencies, and so that's very important. For those of you who remember the movie Contact with Jodie Foster, she begins the movie at the Very Large Array, or the Jansky Very Large Array in New Mexico, which has never been used for SETI research until this year. And this year there is a major program with the Seti Institute to finally use what's the most powerful radio telescope in the world, the VLA, to actually start monitoring the sky for narrowband signals. And it does it in a very interesting way. It's a sort of a piggyback way, where the VLA will be doing other normal radio astronomy research. They'll be looking at a galaxy, they're looking at a black hole, a binary system or something. But because the field of view is wider, if there are stars of interest from a SETI perspective within that bandwidth, within that reception, then you can actually sort of siphon off, if you like, some of the radio signals around the main observation. It's called commensal observing, and so this is something that's going to be done with the VLA moving forward, which is very exciting. It actually really hugely increases the potential for radio astronomy. Those are the big players. I mentioned optical SETI, which is very, very interesting idea, and this has been done a little bit with a couple of optical telescopes. And the idea here is, we would communicate with narrowband radio signals. It's great because radio waves travel, first of all, our atmosphere is transparent to radio waves, otherwise you've got to stick the telescopes in space. But optical signals might also work. So these are narrowband like lasers, which are monochromatic, single frequency transmissions. There's also an idea, and again, going back to the Breakthrough Foundation, Breakthrough Starshot, where there's a possibility of powering microsatellites, microprobes with high energy lasers, laser pulses, to accelerate them up to 0.2 the speed of light, to send them on interstellar
With a space sail or something.
With a space sail, correct. Those laser systems have to be very, very powerful. And in theory, if they are pointing in the right direction, these laser pulses are detectable from the Earth. And so
to what distance?
That depends on the laser that you have, and I haven't got the numbers in front of me. But you're to, let's say few hundred light years.
Oh wow!
So you could pick up maybe a few thousand, maybe a million star systems that way, provided they are beamed at you, which is another issue. You need to have them pointing at you. So either they're deliberately pointing them at you, which is great, which means they know we're here, which may or may not be great, or we happen to be lined up. And so monitoring these very short duration monochromatic laser flashes is a possibility. And the Seti Institute now has a set of what we call laser Seti installations that are going to be put around the globe. And so you get 24/7 monitoring of the night sky for these very short-term laser flashes. These are very, very simple, small-scale cameras with fast readout chips with a wide field lenses.
And they're looking they're looking in a specific wavelength, or they're looking in the broad wavelength?
They'll yes, again, you'll get the light in, you'll bounce the light off of a diffraction grating, so you can actually look at various frequencies to look for these flashes. So the processing, the technology is very basic. It's the processing of the signals coming in, the fact that you do a fast refresh rate that is the advancement there. And so this will allow you an all sky monitoring. It's also very good at picking up meteor showers, obviously, because these are short-term flashes of light. It's a great meteor monitoring. It would also be an amazing UFO monitoring system, because you've got an all-sky visual monitoring, and you can pick up unidentified flying objects, UAPs. Now, that's not suggesting we would do that. Nevertheless, UAPs, unidentified aerial phenomena, as a transient, non-repeating system are very, very difficult to monitor. And maybe there's some interest in that, but primarily we're looking for these sort of laser flashes.
You would need to exclude the ISS. You would need to exclude I don't know, what's the name of those? The Elon Musk satellites,
the Starlink,
the Starlink satellites.
Yeah.
And then there are those phone satellites that you can see from
the Iridium ones.
The Iridium ones that you can see from down here. You need to exclude more and more satellites, but you can do that with software because you know where they are all the time, so that's easy.
Yeah, and that's a very, very good point, and that's the same in the radio realm as well. When you're doing a sky survey with radio telescopes, you are picking up everything. You're picking up cell phone signals, you're picking up satellite transmissions. Most of the false detections have been satellite downlink transmissions. There is so much noise in any part of the spectrum now, and the advancements are the fact that the initial scan of the data can now be done by a machine learning AI systems, so that the humans don't need to be involved until you get down to the very, very interesting signals. And I think that's very, very important, both in optical and radio SETI searches, is that you'll get a million detections a day using a radio telescope, and all of those are what are called RFI, radio frequency interference. They're going to be cell phone towers, they're going to be planes going over, they're going to be satellites going over, and you just don't have you can't employ enough people to sift through that amount of data. And so using machine learning techniques where the computer will identify what a satellite downlink looks like, will identify what a plane will look like, and can sift that stuff out, so that when you come to the end of the day and there are 3 anomalous signals that don't fit into any pattern, that's when you bring the human in. And that human will then say, yeah, well, obviously that's, that's the ISS. Or obviously that's because somebody was using a microwave to cook their breakfast this morning, which has happened.
I think the ISS is the easy one because you know where it is.
Precisely.
The good thing is that you're going to have a very big data set that you can train your machine learning model on, because you have all this information coming in, and you can tag it and say, we know that this is a plane, we know that this is the ISS. And when you have a big data set like this, then you train the model, and it knows, it learns that this is, this type of information or data is ISS, this one is something else. Yeah, so that's cool, using machine learning for that.
Yeah, absolutely. And you have to do that now with the amount of data that's coming in. If you're going to do this well, I think, the early SETI searches failed, obviously. Well, not a fail, but they were negative results. That's not a fail. That's a data point. But the bandwidth that you are searching, the number of targets you're searching, is so small. It's like I don't know, touching down, going to a city for the first time, and you walk down one street and you haven't found a Thai restaurant, and so the conclusion is that there are no Thai restaurants in the city. You really do need to do a much more in-depth search, broad wavelength search, number of targets, deeper searches, before you can say anything about the statistics. But when you start doing that, the amount of data you are collecting cannot be analyzed by humans. And that is the big shift now, the fact that you can remove all of this stuff out, so that humans can focus on the ones that really don't fit any patterns.
So maybe let's talk a little bit about the base of all of this. And you talked about Frank Drake and Drake's equation. So can you tell us a little bit about Drake's equation and how that is the basics to everything that we're talking about right now?
Sure. And what I could do is share my screen so people who are on visuals can actually see this, and then we can run through and talk about the Drake equation. I'm going to do that, and I'm going to go full screen. How does that look for people? Can people see this?
Yes.
Oops. And of course, it's a slide set, not for this talk, but for another one. But I had this lying around. This is the Drake equation. It was an equation, and it is an equation. It is balanced. It does work. So, like all equations, the terms on one side of the equal sign have to balance the other side. So it is an equation. However, it was not designed necessarily to plug in the numbers, although people do plug in the numbers. It's really a thought experiment, and it was put together by Frank Drake for a conference on SETI back in the early 1960s. I think 62, 63. And the idea is that you are asking a question that is effectively impossible to answer, which is n equals, that's the number of civilizations in our galaxy that is possible to communicate with. And that is something you can't, there's no way you can plug in a number there unless you really believe that n equals 1, which is us. You assume it's greater than 1 or greater. But if you start breaking this question down into manageable components, you can start getting an estimate or a range of estimates for that unanswerable question. And we can just run through the terms here, and some of them are easier to answer than others. They get trickier as you move from left to right. The easy ones are the first one. First one is average rate of star formation in our galaxy. How many new stars are being born every year? And that's known very accurately. It's about 3 to 5. Our galaxy makes new stars every year, so that's fine. The fraction of those stars with planets, this was unknown 20 years ago. But now I think the answer is the fraction is all of them. Effectively, unless some of the more extreme stars, some of the very, very bright, hot O stars, as astronomers call them, probably would not have planetary systems. And even if they do, those stars are going to blow up in a million years anyway, so it doesn't matter. But most stars in our galaxy appear from observation and statistics to have planets. So we know that one now. The next one is, of those fraction of planets, which ones may develop an ecosystem? That is, which ones are Earth-like? That's why it's N subscript E for Earth-like. Now, that raises an interesting question about what do we mean by Earth-like? The moon Europa around Jupiter has a subsurface ocean. That might fall into this category. Venus, you'd think, would fall into the gas category, but it doesn't. So you know, again, you can play around with these, and there's room for maneuver. But what's interesting is, with the latest results from the Kepler mission and the TESS mission, is it turns out that most of these planetary systems, once you can study them well enough, do have rocky Earth-sized planets. We won't say Earth-like, but we'll say Earth-sized planets going around them. So again, we're starting to build up numbers that work for this term. Then it starts getting tricky, because of those Earth-like planets, what fraction actually will have life developing on them? And this is where everything falls flat, because we do not know. And this is why the search for life on Mars is so much more important than just the search for life on Mars. Because if you find the evidence for fossil life, as it probably will be on Mars, because Mars is pretty dead at the moment, and there's proof that that life emerged independently of life on Earth, which is not necessarily so. The two planets are so close together, they exchange rocks all the time. But if it's proven that it did have an evolution of life independent and a completely separate biology from Earth, that is amazing for Mars, but it has huge implications. Because if you can have two planets in the same solar system that develop life independently, how that changed statistically for the possibility of life developing on other worlds and other planetary systems is immense. So that's a very important thing. That's a study of astrobiology in that term. Intelligent life. What do we mean by intelligent life? Humans are sometimes intelligent. Whales are intelligent. Dolphins are intelligent. Bees are intelligent in the sense that they can communicate with each other in a sort of hive situation. So again, we need to figure out what intelligent life is, because there's various aspects of that. But the next term is important, because just because a species is intelligent doesn't mean you can communicate with it. I mean, the whales have incredible social systems, but they are not building radio telescopes. So we are not going to be able to communicate, as far as we know, with whales on other planets. So there's a very big distinction between an intelligence and a communicating intelligence that's very, very important. We have, you know, a dozen intelligent species, maybe more, depending on how you define it on Earth, but only one of them can communicate with other star systems. And the last term is the weird one, and that is L. And that is, how long on average will an intelligent civilization be able to communicate? Now, there's two answers. There's an optimistic answer and a pessimistic answer to this. The pessimistic answer is, how long will it take civilizations to blow themselves up, or to destroy their planet? And obviously there's issues that humanity is dealing with. It's all seriousness, we're dealing with this now, with not only sort of a nuclear proliferation, but also with climate change and the effect that's going to happen. But there's another aspect of that, of course, is that civilizations could become advanced enough that we don't know how to communicate with them. They may be using very, very directed pulsed X-ray beams that even if we saw them, we wouldn't be able to recognize them. They may modulate gravitational waves, which we would not be able to understand. So it's possible that a civilization will be fine and be great and everywhere in the universe, but their method of communication, just like somebody from the 18th century would not be able to intercept a cell phone conversation between two people, if they were out of sight. So that this last term L is one of the critical ones. And at the moment, because we have a sample size of 1, that becomes a very, very difficult. You can't do science with one data point on a graph. And that becomes, as I say, as you move from left to right, these things become much more difficult to assess. But the Drake equation I said was a thought experiment. Some people use it as a real equation. You can plug in those numbers and it does balance. But really, it's showing you different ways that science can approach this very, very big question, and using different types of science to do it, using microbiology, using planetary science, using astrophysics for the first few terms. And then for the last term, you are really bringing in it's a reflection, if you like, at the moment of us as a representative of an L. That's very, very important to think about.
So let's maybe talk a little bit about those different types of science fields that are used in SETI. We talked a little bit about something that's more of engineering, which is big antennas looking up. You talked a little bit about biology, exobiology. What else do we have there?
I think the science of exoplanet searches, so missions like Kepler and TESS and James Webb Space Telescope that the collective fingers crossed will actually go up on the 22nd, go up in a good way on the 22nd of December. I think that the exoplanet research holds a big key to the center of the Drake equation. Identifying how many Earth-like planets there are, maybe getting an idea of the atmospheric conditions on those planets. The JWST will be able to look at the spectra of large planets, not Earth-like planets, to look at atmospheric composition, what's in the atmospheres, what type of molecules are in these atmospheres. You actually need a next generation beyond JWST to start doing that for Earth-sized planets. But what you're doing there is you're building up an idea. It's like each planetary system is like an island and an archipelago. We live on one, and we know there are birds and there are rabbits and trees and everything. And you look out to the horizon and you can't see anything, so you build a telescope, and then you can see that there are islands there, and that's great. But then you need to think about what's on that. Are those islands like ours? Do they have trees and forests? And so you need to identify trees and everything, to the chance of identifying whether they have smaller humans or birds or anything. We haven't got the technology to do that yet, and they're certainly too far away to go there. So that's probably a horrible analogy to use. But I think building up an inventory of planetary systems and having much more information about the numbers of planets out there, the number of Earth-sized planets, and getting an idea of the conditions on those planets will really set us up. And the next step, of course, is once you identify, you look at a planetary system and it has an Earth-sized planet going around a sun-like star. Again, this is very sort of anthropocentric, but that's the only thing we can go on at the moment. Sure, you want to look at that planet, you want to point JWST in that direction, maybe get some idea. You can maybe get a sort of idea of a seasonal shift, know if that planet is rotating or not rotating. This will give an idea of things, maybe some clues about the atmosphere. But you can also point a radio telescope at it. And now, once you know that these planets are there, you can actually start pointing your dish at specific star systems. And that's going to be very exciting. When larger radio telescope arrays, there's what's called the Square Kilometer Array, which is a very large radio telescope system that is being built, and very, very powerful collecting.
Is that the Chinese one? There's a huge Chinese one.
There's a huge Chinese one called FAST, which is a large single dish. So that's great as well to do. But The square kilometer array is a collection of smaller antennae that's being developed in the southern hemisphere. So, you know, with these new technologies coming online and knowing where these planets are, that you can really, you know, start being strategic in your search rather than just doing an all sky survey. And so that's really going to change things. So I think getting an inventory of planets is a SETI search. It's not just a planetary science search. And I think also the study of intelligence, what we mean by intelligence. We have a scientist at the Seti Institute called Lawrence Doyle who looks at whale communication. And he is a physicist, but he goes out with biologists on boats, and he listens to what the whales are saying. And they've got to a point where they can actually identify arguments between whales when they these are humpbacks, and they do this bubble net fishing. They release bubbles, and so that corrals fish, and then they can eat them. And they can understand the communication between the whales and various things about what goes right and what goes wrong. Now, we can't get the subtleties of that, but what you're doing there is you are understanding the syntax of an alien species, if you like, even though they're so closely related to us, they're still effectively. So what does that mean? Well, it means that if you do pick up a signal from another star system, you may never know what they're saying. Yeah. But, we can't, you can't try unless, unless you learn, or you have to, you can see Chinese characters if you're a Westerner, or if you're Chinese, you see a sort of Greek alphabet and words. You may not know ever what's being said, but you know that something is being said. You know that there is it's not just a random set of signals caused by a natural process. A starquake on a neutron star will release a set of signals, but there's no pattern, there's no syntax to it. And so what the ability of this understanding how whales communicate is that if you do receive one of these, once your artificial intelligence has given you, this one that doesn't fit into any of the other patterns, it could still be a natural phenomena. But if you can then read a time signal of the variation of that radio signal coming in, you can tell whether there's information enclosed in that signal, even if you never understand what it is. And so I think that's very, very important when this detection comes in. And that's what separates it from, the pulsar signals, which were thought to be artificial, but they're not. Fast radio bursts, which are, again, are thought to be some form of neutron star effect, which initially were thought to be artificial, but they're not. In the end, it's taking a signal and recognizing that there is a communication process going on that cannot be natural. And that is where work with non-human communication on Earth becomes very, very important. So that's a really big deal as well. So you gave different examples, and I'm guessing that these examples fit into the different research centers that the Institute has, because right now we talked about SETI in general, but let's kind of focus about the Seti Institute right now. Mm-hmm. Yeah. Tell us a little bit about it. How is it built? What research centers are there? Who is actually paying for all the research there? You said that, that the government is not. So who is? Yes. Yeah. Well, who's paying for it? Yeah, we can't tell you that. It's the aliens. No. As I said, the SETI research itself is not government funded, and that has to be at the moment through private foundation money. Individual payments, individual donations. Obviously, some individuals can give more than others, and so have more. Paul Allen obviously was an individual who had more ability to give than others, but we get small donations from anyone in, and they can specify that can go to the SETI area of research. So that's how that works. 80% of the work at the Institute is actually falls into the category of planetary science or astrobiology. Let's put it that way. We have a lot of scientists who are involved in the Kepler and TESS missions, looking for exoplanets. We have a lot of scientists involved in Mars missions, looking at the conditions for life on Mars. We have a lot of scientists who are doing what is called Mars analog or Earth analog work, that is studying the conditions on Earth to see what conditions we might observe on Mars. So there are parts of the Earth, the Atacama Desert in Chile is an incredibly arid desert with very high altitudes, receives a lot of ultraviolet radiation, very high UV levels. And these are conditions that sort of mimic the conditions on Mars. And what you can do, of course, is you can look to see, and the Atacama Desert has life everywhere, you know, but it has to be under rocks, you know, protected from the UV and the conditions. And so what you can do is you can look at how life exists in these extreme conditions on Earth. And that gives you an idea of where to point your rover when you're on Mars, because you might think that these are similar areas on Mars. So there's a lot of Earth and Mars analog work going on at the Institute.
We have one in Israel as well.
Yeah. So you know, any of course any sort of extreme environments, you know, are very useful, because you know we have this planet that does have extreme conditions, and yet those in the Antarctic, you know, the Arctic, the deserts, the high mountains, the deep oceans, very extreme conditions, and yet life is everywhere on Earth. And so that will give us a clue as to how to design the next missions to go to other worlds. A lot of that is NASA funding. NASA does fund a lot of astrobiology, a lot of planetary science, and most of our funding, therefore, is government, federal funding. The National Science Foundation as well funds some of the radio work. But so yeah, we are funded by the US government a lot.
And that research is part of the Carl Sagan Center? Correct,
yes. We have divided the Institute into three centers. Center for the research center called the Carl Sagan Center for Research. And we have about 105 scientists working in that center across right along the Drake equation, from star formation to the work on intelligence. And you know, I think we do need. We are thinking about how we would work with other groups like sociologists and anthropologists to talk about the L variable at the end. I think that's a very important thing. We have a Center for Education, which I'm director of, which tries to, you know, works with schools, works with teachers, works with colleges to integrate Seti science into the curriculum, you know, make it accessible, because obviously what we want to do is train the next generation of scientists to come in. And then there's a Center of Outreach, which is to talk about the work that Seti is doing through its webcasts, on its website, and so on. There is a division, it's an artificial division of scientists within the Carl Sagan Center. We have a lot of, you know, the Mars people do their thing, the planetary science people do their thing, but really it's a way of getting this multidisciplinary area together, because it's only bringing these different aspects together, both astronomers and biologists, if you like, and chemists, to actually get the big picture and try and interpret what's going on.
So you talked about the outreach a little bit, or you mentioned it, and I remember when I was younger, there was a project called Seti at Home. Mm-hmm. Is that thing still running? Can you tell us about, maybe for the younger people that don't know what it is, can you tell us a little bit about it?
I can certainly tell you, and I could also lie and say that Seti at Home was a product of the Seti Institute, but it wasn't.
Okay, fair enough.
But Seti at Home was created by UC Berkeley, and it was a way to take data that was received from radio telescope observations and to use your own computer as a as a processor to filter these results as they come in, because of course, as we're dealing with very, very big data sets at the moment. The project is still running, although it's sort of an archive level. It's not really being developed anymore. There is talk about redeveloping it and making a more modern version of it, a SETI at Home 2.0. Although there are issues there, and a couple of issues. One is it was a passive system. That is, the user, the computer, played no role at all in it. It just used up your CPU time. And it would be nice if that person acting as what's called a citizen scientist could actually do something rather than it just taking up your CPU. The problem is, of course, the very, very large amount of data that's coming in. And, we talked a little bit, maybe you can get a mobile phone version that would have some level of interactivity, but it's very, very difficult to do this. It's a technical challenge. So there are discussions going on about resurrecting the idea that data coming from the telescopes would actually be viewable and in some ways sort of processed by individuals who would like to be involved. It was a great program. I ran it on my computer until they told me to stop using it because Harvard decided they did not want outside data going through their machines. So
because you probably needed Windows 3.1 or something.
So it was a great program. I think the two downsides at the moment was it's a passive system. We'd like it to be an active system, an involvement in that process, and the sheer amount of data is an issue, and how if you do siphon off some of that to make it practical to use on people's individual devices, how that makes it a valid research proposal and not just a fun thing to play around with. So it's a great thing, but it's problems at the moment how to update it.
Well, I'm going to follow up and see what happens with that.
Sure. Yes.
One last question before we go to the Q&A section. So your offices are in Mountain View, California, in the middle of Silicon Valley, just beside, Google and LinkedIn and HP and other big companies. Is there any cooperation between the Institute and all these, giants?
Oh, we would certainly like them to help out their poor neighbor down the street. There is a program that runs during the summer. It's called the Frontier Development Lab. It's a machine learning research summer program for postdoctoral students, where experts in machine learning and experts in a particular science discipline come together to try and solve a problem. An example would be how to better model floods from rivers to make flooding more predictable. How to search all the information about exoplanets to make better optimal discoveries of planets around other stars, these sorts of ideas. And there has been a lot of involvement, say, from Google, who have helped out with cloud computing and processes like that. NVIDIA, another of our neighbors who make chips, have helped out as well in supporting this program. But obviously, it would be much better to get them more involved because of the resources they have. But these are ongoing discussions. Yeah.
Okay, cool.
Yeah.
Thanks. So I think we're ready to go to the Q&A. I'm going to open the chat here and see what questions we have. So Neil is asking, does SETI try to research in other ways beside radio signals, like, for example, new ways to understand an exoplanet's atmosphere structure that may indicate of a possible Earth-like planet, H2O, oxygen, etc.?
Yes, I mean that would be ideal if we're in a situation where you could do a look at the spectral signatures of planets Earth-sized planets. Very, very difficult to do. Earth-sized planets are very small. Even JWST is not going to have the capability to do that. But ultimately, yes, that's what we would love to do. And not just the Seti Institute. I mean, there's lots of people who are trying to figure out how to do that. Goes back to this idea of artifact searches, where you can look at much larger scale variations to look for things like large-scale structures. There was an example a few years ago. It's called Voyagian Star, that some of you may have heard of, where just to take one step back, how do you discover planets around other stars? You can't see planets, they're too small. But what you can do is, if you have a nice alignment where that planet goes in front of the star, from our perspective, the brightness of the star dips by 1%. Very, very small. You can't notice it dipping, but if you monitor the brightness with a space telescope like Kepler, you can detect these very slight dips, and you can look at those mini eclipses or transits. And from that, the size of the dip, the duration of the dip, you can get an orbit, you can get the size of the planet, you can even get some hint of an atmosphere from it. But the dip is very, very small. Now, this one star that was observed didn't just dip by 1%. It had these huge dips of 20%, 30%, very, very randomly, huge brightness variations. And one of the ways you can do that is if there is a very large megastructure, that is a Dyson sphere being constructed, happened to pass in front of the star during that period. And for a long period of time, this was a valid possibility. Theory, yes, theory. It turns out that not proven, but large cometary clouds. We have a large cloud of comets in our solar system called the Oort cloud, but large cometary debris would produce a similar and better matching effect on the results. So that didn't work. Nevertheless, it got people very excited, because you could possibly make these detections. And that is something, as I say, one of our astronomers, Anne-Marie Cody, is actually looking at TESS data, not just for that. I don't think NASA would have been very happy. Nevertheless, they're looking for anomalous light curves in other stars. And so that is very much an ongoing investigation that's very, very exciting.
Okay. Next question, Ronnie Kowalski is asking, what is your explanation of the Fermi paradox? Could be a dark forest out there?
Oh, again, it's always difficult, and everyone, I think, has different viewpoints of this. It's working with.
Do you want to just say what the Fermi paradox is?
The Fermi paradox was a comment from Enrico Fermi, who was a great physicist and worked in nuclear physics back in the 1930s and 1940s. And one of there was a discussion on alien civilizations and trying to find alien civilizations. And his question is, well, if they're out there, where are they? Because at some point, you know, we should have found something. There should have been some evidence. And the question is, why haven't we? And there's a whole range of reasons why they're not. Some are more sinister than others. One of the more sinister ones is, if you get a civilization advanced enough, then they are going to remove any potential threats and competition. And a very advanced civilization could do that robotically. There are arguments that in a very short period of time, a very advanced civilization could robotically colonize the entire galaxy. And colonize in the worst possible way. And as humans, we know that the colonization rarely goes well for those being colonized. There are other arguments that, you know, that we are, you know, not being contacted because the advanced civilization thinks we should be left alone, the sort of, you know, Amazon tribe idea that you just let people evolve and you don't disturb them. And there's a possibility that there's nobody else out there. And that is another possibility. The fact that we are, for whatever reason, the the only advanced communicating civilization in our galaxy, which is that again depends who you talk to. I think the problem is, again, having a sample size of 1 for evolution. We only have 1 example of life. We are related to trees and mushrooms and snails. We're all one genetic line, and so it's taken 3 billion years, slightly more, to go from early single-cell organisms to communicating civilizations. Is that normal? Maybe that's fast. Maybe it's slow. Maybe we're the last ones out there, and they're just saying, "Oh, the people on that planet, ignore them. We're not even going to bother. We're just going to pulse our communications and miss them." Or it's very fast, and on average, it takes 5, 6, 7, 10 billion years for civilizations to evolve, and so we're one of the first. We're the pioneers. But it's very, very difficult to speculate when there's no other data points, and I think that's what the SETI search does. Is the more you search and the less you find, the more constraining you're putting on these parameters, and you hope you find something.
So just in that neighborhood, Roy and Eve's question, how come we haven't heard how come we haven't heard a regular administrative message between aliens? It seems we are waiting for a hello humans message.
Mm-hmm. Yeah, again, we're sort of imposing human behavior, best and worst human behavior on communications. We want to reach out to people because we are a communicating species. We love talking. We're doing it now. And yet we're also a species that, sometimes you don't want to let people know you're there because you're going to be taken advantage of. And so it's this dilemma. But these are imposing human value systems on another completely independent civilization. Maybe that it's not normal to communicate. Maybe there's no reason to that nobody's interested in other civilizations. There may be curiosity, which sounds probably a little bit weird because curiosity is an evolved skill. You need curiosity to survive, but you don't know, because again we're dealing with human constructs here to try and impose that on others. Certainly, in order, the Earth has been leaking radio waves since radio transmission started. And I think it's something every day 2 more star systems become, are reached by the signals going out. But this signal becomes very, very weak, very, very quickly. And you are only going to reach a few thousand planetary systems. And if alien civilizations are reasonably rare, the statistics are nobody's going to sort of pick up our signal. So what you're talking about is a beamed transmission, which means you can, if you beam, if somebody had a radio telescope the size of the Arecibo dish in Puerto Rico, which was a radar, it was a transmitter as well. It was they mapped asteroids and things like that as a practical thing. But if you have an Arecibo dish and you aimed it at a star across the other side of the galaxy, that's 100,000 light years and passing billions of stars, and they had an Arecibo receiver, they would pick up your signal. Now it takes 100,000 years to receive it, so there's the practicalities there. So I think so you're absolutely right. To actually communicate with enough stars to be statistically successful, you do need a beamed signals. You can't just pick up random noise. And of course, humans aren't leaking radio transmissions as much because we're using fiber optic cable to communicate, and fiber optic cable doesn't radiate radio waves. And so advanced civilizations probably aren't leaking radio signals because they have a much more efficient ways of communicating. So you're not going to pick up these random signals for advanced civilizations. So that's a limitation as well. So I think we do need to announce our presence, and others need to announce their presence to us in a deliberate way, and that raises all sorts of philosophical and questions.
Next question by Federico Neyman. He's asking, is there any other equation besides the Drake equation? Well, there are tons of equations in physics.
There are tons of equations in physics, and there are variations on the Drake equation, and there's always a suggestion. Why don't you add this term? Why don't you add that term? And it's true, you can fine tune that equation, but that I think that takes away the point of the equation, which is not to get an answer; it's to get a thought process and a roadmap to answering your question. I think it's a unique equation. I think the Seti Institute can claim that it's the only institute in the world that has its own equation. Maybe Cambridge can claim F equals ma, and Princeton can claim equals mc squared. I don't know, but you know, it's I think, and I may be proven wrong, it's quite a unique equation in what it's trying to do.
Yeah, and I think E equals C squared is ours, because he was Jewish and he was, you know.
Yes.
Ronnie Kowalski is asking, are you regarding finding life in our solar system in the next 20 years? Are you do you think we're going to find life here in the next 20 years?
There are a couple of missions coming up that are very exciting. Three that are very exciting. One is Mars sample return, which is a plan to return samples back to the Earth from the rover. At the moment, is collecting samples and depositing them. Possible return 2035. So then you actually can do a soil analysis in a lab on Earth. That'll give you a great handle on Mars conditions. There's another mission called Europa Clipper, which is an orbiter that's going to get really close to the ocean world, ocean moon Europa. Mm-hmm. Which will give us clues as to the structure of the internal ocean, and possible signs of organic materials on the surface. And there's one called Dragonfly, which is going to put basically a drone down onto the surface of Titan, which is a big moon of Saturn. None of these can. I don't think the Mars sample return could possibly prove the existence of fossil life if there are samples in it. I don't think any of them will prove or disprove life in the solar system. But what those missions will do will really constrain the possibilities, because they're visiting the three worlds that the most likely worlds to have life. And if those three come up with very negative results, then I would say that it's not looking good for life elsewhere in the solar system. But if there are possible signs, not proofs, of the conditions on Europa, the conditions on Titan, and maybe some very strong clues on Mars, I think of the three, Europa is the best bet. I think good result there within 20 years, and then putting a lander on Europa and possibly a submersible to get into the liquid ocean. That's the way to go. So I don't think we'll be sure there's life in the solar system in the next 20 years, but I think we'll have a good idea of being optimistic or pessimistic, is my prediction.
We're going to stay for now optimistic.
Yeah, absolutely. Yeah.
Ariel Cohen is asking, what would you say was the most promising signal we have ever received?
Oh, that's a very good question, and it depends who you talk to. I think the one that they had very, very recently, which was called BLC1, Breakthrough Listen 1, was very, very exciting for a while. And this was a result from the Parkes radio telescope. They have a very big radio telescope in Australia. Done a lot of work on things like quasars and things, but they do SETI work. And in April of 2019, they picked up a signal, a very narrowband signal, in the direction of Proxima Centauri, which is the closest star to us. It's a red dwarf. And it passed a lot of the tests that are put in place for, is this real or is this not real? That, you know, machine learning, this is one that all the machine learners, the artificial intelligence thing would spit out and say, humans take this one and play around with it, because it had all of the characteristics that was being looked for in a signal. Is a very narrow band, which is an artificial, say, an artificial signal. When you move the telescope away from the direction it was pointed, the signal goes away, which is good, which means it's directional, unidirectional. It showed a drift feature, that is the frequency change, because of course you're observing from an Earth that's rotated, going around the sun, and so that means it's not an Earth-based thing. It's not somebody's mobile phone, because then you would not get a drift in frequency unless they're driving a car very fast away from you. There's
like a redshift.
Yeah, correct. So all of these things actually pass the test. And it's not clear, they have not yet determined what it is. However, archival searches showed that these types of signals have cropped up before from human sources, from, say, aircraft transmissions and satellite transmissions. They could not find what caused it, but the fact that it looks like other signals that are human origin signals means that they are not confident that it is a technosignature from Alpha Centauri, but it ticked so many of the boxes that I think people were getting very, very excited about that. And that was a very recent one, and it's a good yardstick. I mean, these are good tests. You know, you want to throw something at the, you want to throw these things at the telescope in a sort of natural way and test it. How good are we at really being very, very scientific? And this is where SETI research differs, say, from UFO spotting. The point here is that you really do whole set of repeated observations and really try to prove that this is not a signal from an alien civilization. You really have to be methodical about it, and not say, well, this is blurred, I don't know what it is, therefore it is a UFO. That doesn't work like that. It goes the other way. You see a blur and you think of all the ways that it cannot be, and you work through that systematically. So that was a very, very promising one. There's the one that's famous called the WOW signal that was detected back in the 70s, and this was a very, very strong one-off, very bright radio source. Again, the problem with the one-off is you can't test it. You know, it comes and goes. It's like seeing a shadow. It's a one-off. You see a shadow in the corner of your eye. You know, was it the Yeti, or was it a dog, or was it a bird, or, you know, who knows? You need to do repeated observations, and you need independent observations. And so, although that was exciting, and it's still, you know, there have been songs written about it, and it's very exciting, but unless it's repeatable, and the location has been looked at many, many times with more sophisticated telescopes. Maybe it was an alien signal, you know. Yes, sure it was, but we can't prove it, and if you can't prove it, it's not science, and you have to let it go.
Yeah, that's true. So scientifically speaking, we have 5 more minutes and 2 more questions, so we have 2.5 minutes for a question.
Okay.
Yuval Cohen is asking, is one of the goals of the James Webb Space Telescope to try and find extraterrestrial life? If so, in what way?
It's not in the goal of the James Webb to find extraterrestrial life. However, some of the observations it's going to make will help us get to that point. It's an infrared telescope. It was designed to look at the early universe. When it was designed, nobody knew about all these exoplanets. So in a sense, it was not designed to look at planets at all. But it has the ability, it's going to be our best telescope in the infrared range. A lot of organic molecules in planetary atmospheres are strongest in the infrared region of the spectrum. It's going to be very, very good, at least the best telescope we have, at getting an understanding of planetary atmospheres. Again, probably not Earth-sized planets, but larger planets. And who knows what it's going to discover. I mean, that's the exciting thing about building a new big telescope is whenever you build a bigger telescope, you discover something. So it's not designed for SETI research as such, but it could really sort of turn up some things that we really didn't understand before. So that I think that's the exciting part of it.
Yeah. Okay, cool. And we've reached our last question by Leo. Is there criteria based on distance from Earth when selecting potential star systems for signal search?
Yes, I think the further away you go, the weaker the signal gets, and that's very, very true for anything. You know, it just you got you've got a light bulb, it's bright in your face, but if it's a mile down the road, it's very faint, and so the signal degrades the further you go. So early SETI searches were specifically with very close by stars, and I think that's going to remain the case. And by very close by stars, we're talking the nearest sort of hundreds of thousands, millions of stars. Now our galaxy has 300 billion stars in it. The only way you're going to satisfactorily do SETI beyond that is if there are beamed signals coming in. That's going to imply either a civilization 100,000 light years away is beaming it at us, which is unlikely because 100,000 years ago, humans were not capable of receiving a radio signal. We're living in a very narrow window. It's not just a spatial problem, it's a temporal problem. We've only been able to detect radio signals for 50 years. That we could have, the Earth could have been flooded with this amazing Encyclopedia Galactica of radio waves 100 years ago, but there was nothing to pick it up. So that's a problem. So yes, I think all of the searches will continue. I think the discovery of exoplanets nearby will get you pinpointed targets. But the nice thing about this new program with the VLA is because you're piggybacking on observations of all over the universe, that you may well be lucky and you're going to pick up these signals that may be, you know, out of nowhere, that you'd never dream of looking in that area, but we can now maybe pick up something random. So that's going to be exciting as well.
So I think, yeah, there's a lot of excitement in front of us, and I think in the space industry in general, everybody's feeling that interesting things are happening right now. More and more people are going up to space. Rockets are becoming cheaper. You know, more science, more citizen science, and hopefully even more than what we have today. So I think with that happy note, we can probably conclude our talk today. So Simon, I want to thank you very, very much for this, for the time you gave us and for this very interesting talk.
It's a pleasure to join you. Thank you very much for inviting me.
Thank you. And of course, thanks to Ronnie for the introduction. And I want to thank the podcast team that works with me and does a lot of, does a lot of work behind the scenes. Aviad Man, the Superman, who is the sound man, and Itai Leon, Don Corleone, who does all the graphics. And of course, Bennett and El, who is cool like Space IL, and he does everything in the social networks for this podcast. Thanks again to the Ramon Foundation and the Horizon community and the Israeli Space Agency for all their support. And last but not least, thank you everybody, all the viewers and listeners who joined us today and listen to the podcast. I'm Ben-Zaav, and this was another episode of al-Khalal, which means in Hebrew hyperspace, but it has a dual meaning in Hebrew. And thank you for everyone, and feel free to unmute yourself, and thanks Simon, and we'll see you in the next episodes.
Thank you.
Thank you very much. It was excellent, Simon.
Thank you. Wonderful questions as well.
Thank you.
Simon.
Yeah.
Will you send me the recording?
Yeah, I just hit stop record, so hopefully
that's good.
Hopefully that recorded. You've still got a record signal on yours.
I am recording.
You're recording. Okay,
Yeah.
good. Okay.
Yeah, so whenever you have time, just I don't know how big that file is going to be. Maybe
Yeah.
send it through WeTransfer or some other service that
Yeah.
sends big
Okay.
files.
Let me see. Yeah, we'll see what happens there. Yeah, we may need to do something like that. That'll be fine.
Okay.
And yeah, no, thank you very much. And you know, as I say, when you're visiting the Seti Institute, maybe we'll turn the tables and we'll interview you.
That would be great. Okay, thank you very much, everyone.
Yeah.
Have a great day, and everyone here in Israel, have a great night. Bye-bye.
Yeah, take care, everybody. Bye-bye then.